Okay, so continuing with torque, let's see what we've got next. This one's a little bit of biology, which is good because I like to try and showcase how the sciences can overlap. So for any of you looking to go into medicine, here's where some of the physics principles actually apply to day-to-day life. Let's see. So in this problem, we say a cook holds a 2.46 kilogram carton of milk at arm's length. Okay, so here's what I'm going to do. We're going to say that this is my arm. So imagine it kind of like this. And I am not a cook, but I'll hold a mallet like this. Now, the way they've got it in the diagram, we've got our forearm level, but our back arm here is actually at a bit of an angle. So we're not holding it straight out like this, we're actually holding it like this. Okay? And they give the following information. Though it doesn't look exactly like this, this is how we want to set it up. So here's my elbow, so to speak, and then here is my upper arm. All right. Now the thing about it is we have a tendon, which is basically, you can imagine it kind of like a rubber band that comes down here and attaches like this. And they've got an angle right here of 68.7 degrees, at least for my question. Don't know if yours is noticeably different. That being said, they've got this right here, this distance is 8 centimeters, at least for my problem. Now, whether or not that's realistic, I don't know actually. 8 centimeters would be a little less than 4 inches. That's over 3 inches, which seems a little excessive to me. So it may be that we've got kind of different numbers and it may not be perfectly realistic. That being said, your tendon isn't going to attach right to the elbow. It's actually going to attach to your forearm a little bit off of the elbow. All right? And then the other thing that we've got is a carton of milk, basically an object way out here, and it has a weight that is pointed down like this. Now, we don't know the weight, but we do know that the mass is 2.46 kilograms, at least for my problem. They've also got it where this distance, see? Yep, is 25.4 centimeters. All right, and they ask the following. We're holding this thing. Okay, what force, FB, the way that they've got it listed there for the bicep, is exerted by the bicep muscle? So I probably used the wrong term with a tendon there. I apologize. It's pretty late at this point, and I'm a little out of it. Also, while I know a bit about the structure here, I'm not as good with the terminology. So we're dealing with the muscle actually holding it in place here. Okay, and so we're trying to find the force applied by the muscle to hold this here. Okay, well, here we go. So what we've got is a statics problem. So, give me just a moment. Here we go. We want our forearm to go out and stay where it's at. We don't want it where our arm is falling down, and we're not trying to chuck the milk into the ceiling. So we want the way this is set up for our arm to stay stationary, which means we've got a natural center of rotation right here, because if my arm moves, it's probably going to be moving around my elbow. On top of that, there are some forces from my bones being connected here, probably by real tendons. There's that terminology that I should probably be better at. But we don't know what forces are actually happening at the elbow. And as we've seen in some of the other static equilibrium problems, the best way to deal with forces we don't know and don't care about is to put our center of rotation there so that they disappear in our sum of torques. In fact, I'm not even going to bother writing down my sum of forces because usually sum of torques is the place where things are going to get easier for us in a statics problem. So I'm going to jump straight to the sum of torques. First off, let's find the weight over here. We know that it's 2.46 kilograms, 2.46 times 9.8. I believe they told us the acceleration due to gravity is 9.8. Yep. And so I find that my weight is 24.11 newtons. 24.1 would be perfectly fine. And here's what I'm going to do. I'm going to do my sum of torques about my elbow. Okay, so I like to start on the left-hand side and move my way in. First force that I come across is this one. Hey, it's the weight of the milk carton. So we're going to say that the weight is 24.11 newtons, and we're going to multiply that by the lever arm, which is the distance from our center of rotation out to where the force is applied. Now here's where you want to pay extra close attention, because a lot of people like to just take numbers that are given to them, and you might inadvertently take 25.4 centimeters, but that's only the distance from here to where your muscle is attached in our diagram. What we need is the distance between here and the center of rotation, our elbow. So what we need is 25.4 centimeters plus 8. That comes up to 33.4 centimeters, which I'm going to call 0.334 meters. Now, on this one, we've got that my force is pointed down and my lever arm is pointed to the left. The angle between these is 90 degrees, so I've got sine of 90 degrees. Finally, the last thing that I like to do is I like to check which direction we're dealing with. Here's my center of rotation. If this is the only force acting on it, it would make it spin down this way, which is counterclockwise. So by the convention we use in class and the standard convention, this is a positive torque. Okay, great. We've got this one done. Let's move across. Any other forces? They don't actually give us the mass or the weight of your forearm, so we're going to ignore that. But in real life, that would be something that we'd have to take into account. And it may not be in the exact middle of your arm, but it would be somewhere in there. For now, we're going to ignore what goes on for us having to lift up our own arm, but that is a real thing. It's not like if you do this, you can do that all day. You're eventually going to get tired and put your arm down. That being said, the implication on this problem is we're not going to incorporate that, and that sounds fine. So here's what we're going to do. Now we need, our next force is going to be of the muscle. Now the muscle is pulling up, back up that way, the bicep muscle. So this is our FB. It's the thing we're actually looking for. So we've got the following. We're going to need plus or minus, we'll get to that in just a moment, but the force of the bicep times its lever arm. Well, its lever arm is right here. It goes from the center of rotation straight out to where the force is applied at this point, and that is 8 centimeters, 0.08 meters. Here's another thing that we need. My lever arm points to the right, and now my force is pointed up to the side. There's this angle between them. Now, you'll probably be fine if you just use the 68.7 that's given to you, but technically our angle is this. Because our lever arm points this way, and our force is up like this, we've got an angle here of 68.7 and 90 degrees, so the total angle is 90 plus 68.7, which is 158.7 degrees. That is technically the angle we are supposed to use. Now the nice thing about the torque equation is most likely if you use 68.7, in fact let's double check. Mode, I am in degree, which is important because I'm going to be putting degrees in. Sine of 68.7 is 0.931 and sine of 158.7 is, oh, glad we double checked this. This is one of those instances where that angle is not the same. The sine of 158.7 is 0.363. I can't believe I almost assumed it would be the same. It's actually this angle. And so I'm glad we double checked that. Never be afraid to double check the angle between them. My force points up this way and my lever arm is this way. So my angle is 158.7. I almost went with 68.7. I almost made a mistake. It happens. But we want to avoid that. So we need sine of 158.7 degrees. This is one of those instances where we need to include the sine of the angle. Because it's easiest, like we talked about in class, like when you're opening a door, it's easiest to push directly into the door. It's hard to pull it at an angle. Those angles are important when it comes to torque. All right, now we need to find out if this is positive or negative. So here's my center of rotation. This force is pulling up at an angle like that, so it would pull it up like this, making it rotate clockwise. meaning it is a negative rotation. Right? And then the only other forces we have are at the elbow, which is at our center of rotation. So whatever forces are there, do not apply a torque. So these have to add up to be 0 in order for the arm to stay where it's put. Okay, great. That gives us the following, that we end up with 24.11 newtons times 0.334 meters times sine of 90, which is just 1, is equal to, I'm going to add this over to the other side, FB, the force of the bicep, times 0.08 meters times sine of 158.7 degrees. There we go. So I want to solve for FB. So I'm going to take 24.11 times 0.334, 0.334. All right, that gives me my torque. It's 8.053, basically. I'm going to divide that by 0.08 meters, 8 centimeters. And then I'm going to divide that by sine of 158.7. And I get the following. If I've done this correctly, the force that my bicep must apply is 277.1, but 277 newtons. Let's double check and see what they've got listed for the answer. 277.084 newtons, so 277 newtons. That is our correct answer. All right. So this is how we go about applying statics onto a, well, real-life system. We've been doing quite a bit of that, but here's one that's in the biosciences. This gives you an idea of what strain or what force you have to supply with your bicep muscle at a given angle. Now, if I change my angles, I can change what the forces have to be. In fact, if I lift this up, this angle becomes even shallower, or I should say even bigger for what goes in there, and then to compensate for it, the force has to get bigger and bigger, which is why when you hold something out here, you have to, it feels like you have to apply so much more force, and you get tired more easily. As you bring that down, you change this angle, which will then decrease the force, and it becomes easier to hold something down here. And in fact, the easiest to hold is like this, mainly because now, instead of having your muscles hold it up, it's just your arm, your bones being connected. All right.